Howdy. I just wanted to finish our discussion today because the language of limits is extremely important, and I did not want you to walk away from the class without having the opportunity to catch it. So, to go back to our discussion, we said that this language means that f of x is arbitrarily close to L for x close to but not equal to C. And I've done this in different colors here because we're going to do some translation, and I wanted for you to be able to see how the parts match. I'm going to assume that you are comfortable with this definition because we used it all last year. What we did today was to take this definition and translate it. And we did an intermediate translation like this, that the sentence, the limit as x goes to c of f of x is equal to L, means that for any neighborhood of L, there is and I'm going to put the word deleted here, a deleted neighborhood of C such that let's put the word deleted in red here. There we go. So now our colors match. Such that when x minus c is less than the radius of our neighborhood, then f of x minus L is in the radius of our neighborhood also. Now, spend just a little bit of time on the translation so you can see how these two match. The delta and the epsilon in our intermediate definition here represent the radius or the size of that neighborhood. And so what we're really saying is I can choose any radius or any size, hence the words for any, and when I choose that radius or size of the neighborhood around L, it is possible to find a neighborhood around C so that when the x's fit into the neighborhood around C, that forces the f of x's to fit into the neighborhood around L. And we delete x equals c from the neighborhood around C so that we don't have to worry about or consider what happens at x equals c. Hence, we have a deleted neighborhood at C. Just to be clear about this picture, let's take for ourselves an arbitrary f of x and an L here and a C, just like so. Notice that f of c happens to be equal to L, but we don't care about that. we could just as easily draw an f of x such that f of c doesn't even exist. Okay? And the process is now a two-step process. First, pick a neighborhood around L. There it is. And it has a radius of epsilon. And now from that neighborhood around L, let's see if we can find a neighborhood around C. It looks like we can. If I choose this neighborhood around C, then all of the x's in this deleted neighborhood have the property that their corresponding y values fit into the epsilon neighborhood around L. We're going to do a lot of this tomorrow when we play the delta epsilon game. So if you're worried about how to find these neighborhoods, don't worry about that at this time. The only thing that I want you to see is that this limit definition does this for us. What it says is that x's close to C, here they are, produce f of x's close to L every time. And if this statement is true, then my limit is L. That's what this means. Now, what I'd like to do is to take our transition definition here Oh, let me come back and explain a little bit more of the math symbols so that you can see the correspondence between the language and the symbols. So, here are my x's close to C that are represented in the deleted delta neighborhood of C. And this arrow, the implication is that if x is in this neighborhood, then every time f of x will be in that neighborhood. In other words, x's in the neighborhood of C are forced to produce f of x's that are in the neighborhood of L. Okay. Now, let's take the plunge and take our neighborhood language and fully symbolize that. I want to copy the transition definition down so that we have enough space to read it. Not you. Yep, there. Group all of that. Here's our transition definition. Copy it. And go to the next page here. Boom. And now we're going to turn it into mathematical symbols using Aristotle's universal quantifiers. And there are two of them. And those two symbols are an upside down A, that means for any, or for each, or for every. In other words, for all the ones you can possibly pick. And the second quantifier is a backwards E, which means there is or there exists. Let me give you some examples of usage for just a moment here. If I say for all n, 2n is even, then what this means is that if you pick any possible n, then 2 times that n is an even number. Is that a true statement? Well, it's true if n is an integer. Meanwhile, I can say there exists an n such that n is odd. Is that a true statement? Can I find at least one odd number? Well, actually, yes, I can. n equals 3 would be one such number, but so would n equals 1, so would n equals 5. Right? To make this statement true, right here, it has to be true for every single value of n. To make this statement true, it has to be true for at least one value of n. Okay? Now we're going to use these universal quantifiers to translate our statements about neighborhoods. And here we go. The limit as x goes to c of f of x equals L means that for any epsilon greater than 0, there is a delta greater than 0 such that when x is in the deleted delta neighborhood of C, then f of x is in the epsilon neighborhood of L. This nice little symbolic representation right here, which looks a little strange, is simply translating what we said about neighborhoods. Let's break it down. For any neighborhood of L, we can find a deleted neighborhood of C such that all of the x's in the neighborhood of C produce f of x's that are in the neighborhood of L. You see how that translates? This is the formal definition of limit that we are going to use now. Don't worry at this stage about finding the epsilons and deltas. We'll do that tomorrow and the next day and so on. All we're doing right now is simply translating language. So let me close with an example of translation. Let's take the sentence, the limit as x goes to 1 of 3x minus 1 is equal to 2, and translate this into a statement about neighborhoods, and then a statement about a formal statement. So if I use our transitional neighborhood language, then it's going to look like this. I'm going to identify my L and my C right here, and we're saying for any neighborhood of 2, there is a neighborhood, and you can say y equals 2 if you want to be particular about it. There is a neighborhood around C equals 1 such that whenever x is in the neighborhood, the deleted neighborhood of 1, then 3x minus 1 is in the neighborhood of 2. Notice the roles that are played here. We've got our f of x right there. We've got our L right here. And we have our C right there. And the delta and epsilon are the radii of the neighborhoods around C equals 1 and L equals 2, respectively. So once you've translated it like that, which I usually do in my head, then we can translate that using the quantifiers. For any epsilon greater than 0, there is a delta greater than 0 such that when x is in the neighborhood of 1, then f of x is in the neighborhood of 2. And you may be thinking, couldn't you simplify this? And of course you could. So that's how all this works. We could do the same kind of translation process in reverse. Suppose I saw this statement. For any epsilon greater than 0, there is a delta greater than 0 such that when x minus 3 is less than delta, then that implies that x squared minus 9 is less than epsilon. So I might look at this statement right here and translate it into a limit statement by identifying. First of all, we obviously have a couple of neighborhoods that are defined by the radii delta and epsilon. And it's pretty clear that the x's are going to be in the neighborhood of 3, so that must be my c. And we could represent this guy in a lot of different ways here, but the most obvious would be to represent this guy as L and this guy as f of x. That isn't a unique choice. We could have had x squared plus 1 minus 10 be our f of x and our L, or we could have, there's an infinite number of possible f of x's and l's, but this is the simplest one. And so a way of translating this back into a statement about limits would be to say that the limit as x goes to 3 of f of x is equal to L. Or, if I chose a different f and a different L, then I could say that, or so on and so forth. Well, I hope this is helpful to you. The only thing I want you to focus on at this time is the translation between the formal definition of limit and the limit statement, and the corresponding picture that involves neighborhoods. We would draw a picture of this guy like so. And this is saying that if I pick any neighborhood around 9, then it's possible to find a neighborhood around 3, so that all of the x's within the neighborhood around 3 produce y values that are within the neighborhood around 9. Tomorrow, we'll discover how. See you later. Okay.